So then let's talk about boundary conditions. We'll consider again the same partial differential equation for which we just derived our weak statement. And that looked something like this. We had these integrals, a dot gradient of u multiplied by w, kappa gradient u dotted with the gradient of w. And then we still have this boundary term. And the right-hand side is going to be equal to f times w. So here I have an example domain, right? This is our omega. And right now, the integration that we have right here is going to involve the entire boundary of omega, right? Partial omega. Now, the way that we have to specify boundary conditions well, we have two different types of boundary conditions. We have our Dirichlet type and our Neumann type, and we're going to have to specify both differently. So in this example picture, I've already divided the boundary of my domain into these two different sections, partial omega d for the Dirichlet data and partial omega n for the Neumann data. So what I'm going to do first is I'm going to separate this integral also in these two different boundaries. So I'll separate this into a boundary integral over partial omega d of kappa gradient u dot n times w, and another section that is exclusively on the Neumann boundary. And since the Dirichlet and the Neumann boundaries together are the complete boundary partial omega, I can simply subdivide it like this, and I'm not forgetting any part of my integral. So what is Dirichlet data? Well, Dirichlet data is where we're specifying the solution field itself, right? So on the Dirichlet data, we might say u, or on the Dirichlet boundary, we might say something like u is going to be equal to gd. A function, specified function g and subscript d for Dirichlet. So this is again data. This is a known function. On the Neumann boundary, I have a different condition. What I'm going to say instead is that kappa times the gradient of u dot n, that's going to be equal to some other function, gn, a Neumann function. And now we see that this is precisely the expression that shows up in this integral on the boundary. And of course, that's not an accident. That's why this boundary condition exists in the way that it does. And that's what we call then a natural condition. So a natural condition is the condition that shows up naturally by going through the integration by parts steps. Yeah, so this is the term that we can directly now substitute into this integration. So this is going to be equal to integration of partial omega n. Well, actually, these are minuses. Of my specified function gn times w. Yeah, now this is no longer dependent on u, so I can move this to the right-hand side, and it falls into that linear form on w, right? This is linear with respect to w. Now, I'm still not entirely happy though. I have to do something for this term as well, and that has to do with the Dirichlet data. So Dirichlet data does not show naturally into our formulation. Instead, what we're going to do is this is something that we're going to have to specify strongly. And what that means is that the Dirichlet data is going to be set manually on the space. And in order to do this, we're going to have to define a new space. We're going to have to define h10 of omega. And let me write this slightly differently. I'll write this of omega semicolon partial omega d. Now this is going to be a new subleft space, and I'll define this to be the set of all functions that lie in h1 of omega. Inside. So the functions in h1 of omega. But I have a new condition for it, so I'm going to say such that my function u is going to be equal to 0, hence the subscript 0, 0 on partial omega d, on that boundary. Yeah, so that's going to be a new space. So what I'll first consider is the question where g of d is equal to 0. Suppose Pause. G of D is equal to 0. Yeah, so our Dirichlet data on this Dirichlet boundary is going to be set to 0. So what I can do right now is I can state my weak form as find a function u in, well, then the relevant space is h10 omega partial omega d. That's going to be the space in which my solution is going to live because, well, it satisfies my Dirichlet condition. And I want to find this function such that, and then we have our same integrations here. Integration of omega over a dot gradient of u w plus integration of omega of kappa gradient of u dot gradient of w. But now, actually, this guy also removes because I'll also set all my test functions to live in h10. And if my test functions also live in h10, then this one becomes 0 on this boundary. Right? That's how we define our space. The functions are 0 on this boundary. So then this integration is also equal to 0. So then I'm done with my left-hand side. And on the right-hand side, I'll have f times w plus now also my Dirichlet data. And this can be an integration over the Neumann boundary. And this has to be true for all test functions in h10. D. Yeah. So how long was this video so far? I'm not sure if it says that. Okay, I think, you know what, I'll slice this video up. So, okay, I think that's what I'll do for now. This is how the standard way of treating these boundary conditions, right? So we have Neumann conditions which show up naturally, and we can substitute them and move them to the right-hand side. And the Dirichlet conditions are somehow going to be specified in the space. So now we looked at the simple case of GD is equal to 0. And now I'll create one more video for which I'll actually treat the case where GD is not equal to 0, because that's actually not such an easy case. Yeah, that's something that we have to think about a little bit. Okay.